This is a scatter plot showing a sequence of points bouncing erratically. At first glance, it's pure chaos. But if we fade out the noise, a perfectly smooth, convergent curve emerges from a select few points. When a parent sequence diverges, we can use a mathematical microscope to extract these localized pockets of convergence hidden inside it. Definition 3.5 in Rudin's Principles of Mathematical Analysis provides the rules for this extraction. Notice the restriction. We choose positive integers where n1 is strictly less than n2, less than n3. You must select terms without altering their original chronological order. This strict chronological selection rule is the precise mechanical engine that powers major topological guarantees, like the Bolzano-Weierstrass theorem. Let's break down how this double index notation looks in practice. In this horizontal array, the white numbers represent the parent sequence indices, 1, 2, 3, and so forth. When we select specific terms to drop down, we assign them a new, bright yellow index. That is our k. So nk simply means we are looking at the kth term of our newly extracted subsequence, which came from the nth position of the original. Because our n indices must strictly increase, we can skip elements, but we can never reverse direction. If you select the fourth term, you cannot go back and select the second. This leads to a strict mathematical guarantee. If a parent sequence converges to a limit p, every extracted subsequence must also converge to that exact same limit p. We can see why visually. This geometric sequence of dots eventually enters a defined circular boundary, an epsilon neighborhood, around the limit point p. Because the entire sequence is eventually trapped inside that boundary, any subset of those dots you select is naturally trapped inside the exact same boundary. The real utility of subsequences reveals itself when the parent sequence fails to converge. Consider this 1D number line tracking the sequence -1 to the nth power. The point strictly ping-pongs back and forth between -1 and 1. If we define our index rule as n sub k equals 2k, we isolate only the even terms. By extracting just the right side, we get a completely stable subsequence that converges perfectly to 1. Conversely, if we change our rule to 2k minus 1, we isolate the odd terms on the left side. This yields a stable subsequence converging to -1. Let's test this concept. Here is the complex plane showing the sequence I to the power of n. The point rotates in 90-degree increments around the unit circle. Pause the video now and determine the subsequential limits. Depending on the progression of indices you choose, you can extract 4 distinct perfectly stable subsequences. The limits are 1, I, -1, and -I, located precisely at the 4 cardinal points on the unit circle. Let's tie this mechanics back to the text. Look at Theorem 3.6, Part A, at the bottom of page 51. Rudin states that if a sequence exists in a compact metric space, it has a convergent subsequence. Here is the intuition. This bounded circular area is a compact space. If you pour an infinite number of dots into this finite room, lack of space physically forces them to cluster infinitely close to at least one target point. Now turn to Theorem 3.7. It states that the subsequential limits of a sequence Pn in a metric space X form a closed subset of X. In plain terms, this means that if you have a cluster of subsequential limits, and those limits themselves converge toward a broader target point, that target point is legally guaranteed to also be a valid subsequential limit. The set contains its own boundaries. Let's review. First, subsequences are formed by strictly increasing indices. Second, they preserve limits of convergent parent sequences. Third, they extract localized limits from divergent sequences. Finally, in compact spaces, at least one convergent subsequence is mathematically guaranteed to exist. Subsequences provide a rigorous way to carve out hidden order from infinite noise. If you found this helpful, subscribe to the channel for more step-by-step guides through